Hi everyone, welcome back to a linked list review. In this video, we're going to be reviewing the concept of a linked list, as well as going over a pretty complex practice problem, so should be a fun time. Just to review, a linked list is simply a series of linked nodes. So in the last video, we talked about the concept of a series of linked nodes. Well, the linked list is the same thing, except for we have this front field that points to the very first node in a series of linked nodes or list nodes. And here's like the class definition. It's exactly the same with the list node class nested inside of our linked node class or linked list class with this added front field. Pretty cool, huh? Now let's go over an example of traversing a linked list. And in this example, we're also going to be adding an element of modification, where we want to add a node with the value of 12 to the very end of the list. So we're going to use this traversal pattern that we talked about 2 sections ago, where we're having a while loop and we're checking against some value or node is not equal to null. And inside of the loop, we're just going to be repeatedly setting a current or temp variable to next in order to traverse a linked list. And we're going to be doing the same thing here. However, in this example, instead of checking if cur is not equal to null, we're going to be using cur.next is not equal to null. Since we're adding a list node, we want to stop one short. And to do this, we have to check if current.next is not equal to null. If we use current not equal to null instead, then we would go all the way to null before inserting. And trying to insert into null will not work out nicely for us. We'll attempt to set null.next to a new list node and get a null pointer exception. So we need to stop one early using .next. This is a super common pattern. If it's read only, you'll often go until current is not equal to null. But for modification, we'll go until current.next is not equal to null a lot of the time, if not all. Yeah, let's run through the simulation. So we start at the first node with current equal to front. Current.next is not equal to null, so we set current to current.next. And we repeat this process until we get to the very end of the list. Once current is on the last list node or linked node, the current.next is not equal to null check fails, and we're able to set the next field to point to a new linked node. If we wanted to add a value to the front of the list, um, the operation is slightly different and maybe a little more simple than the other one. We can simply construct a new list node using the 2-argument constructor we talked about with a value of 10, if we want to insert a node with data 10, and give it the next field of front. So now front points to a new list node, whose next field points to the previous front. And boom, insertion at the front of the linked list. There are only 2 effective ways to change a linked list, and that's to either change what front points to or what a .next field points to. If we want to, and additionally, like we talked about, we have to stop one node early when traversing a linked list in order for this change to work, or for us to be able to make a change. If we attempted to use cur is equal to a new list node, so the cur.next, then we're simply reassigning the reference of a variable we created, right? We're reassigning a reference instead of making a change of a node field inside of our actual linked list. Yeah, so this is why we have to use current.next to modify an actual field inside of our linked list instead of reassigning a temporary variable we created to point to some other node while not actually changing the list. And we also talked about cases to consider when solving linked list problems. If, like I said, if these are read-only problems, then cur not is not equal to null will usually work when traversing. However, in modification problems, most of the time they'll be cur.next. We need to consider whether we're stopping at the front, middle, or end of a linked list. because that modification will be slightly different, as shown in the previous example. And there are cases to consider when writing our programs, right? FME or FML, whichever one is more suitable to you. I prefer FME just because it handles the empty case as well, but whichever acronym allows you to remember better is the best. And we need to consider the front, middle, and the empty cases. So the three discussed in part 2 of this slide, as well as empty. Usually, if we don't handle empty, we'll run into some null pointer exception. So always keep these cases in the back of your mind when writing solutions for linked list problems. Let's hop on over to a practice problem from our linked list section. This problem is called remove all. Our task is to write a method, remove all, that removes all occurrences of a given value and returns the number of occurrences that were removed. So if you were given this list with a 2-node, -4, 12, 0, 2, and 2, and we were tasked with removing 2, then we would remove all 2 nodes, maintaining the original order, and return 3, since we removed 3 nodes from our list. And we are writing this inside of our linked list class. Before we begin, let's pseudocode this to kind of give us a foundation of which to build our program off of. So right off the bat, right, we're told that we have to create a count variable to track the number of removed nodes. Let's add that to our pseudocode. Next, we probably know that we're going to be running over the entirety of our linked list. So yeah, traverse through all of our linked nodes, and we know how to do that using our while loop. However, this is a modification problem, so we have to compare .next in order to stop one early to remove nodes as needed. Third, while we're traversing, if cur.next.data, so this next node is equal to the given value, we have to remove it. And this is why checking next is so handy. It allows us to stop one early in order to easily remove the next node in the linked list, as opposed to cur, which would be impossible to manipulate, as the only 2 safe changes are front and changing .next. Finally, we return count. Let's code this up on Ed. All right, everyone, we made it to Ed. I copy and pasted our pseudocode for ease of access, so let's go ahead and implement that. The first step we said was to create a count variable to track the number of removed nodes. Well, we know initially we haven't removed any nodes, so let's go ahead and create that variable and set its value to 0. Next up, we have to traverse through all of our nodes. We know how to do this using our traversal pattern by creating a temporary variable and setting it to the front of our list. And then we just loop through the end of the list by using our null check, and then setting cur to cur.next. This is close, but like we said, we need to check if cur.next is not equal to null and not cur, since we wanted to stop one early. So let's go ahead and do that. While cur.next is not equal to null. Step 3 is if cur.next.data, so if that next node has a value that's equal to the given value, then we want to remove that node. So if cur.next.data is equal to val, we want to remove that node somehow. How can we remove a node or the next node from a linked list? Whoa, we can use references, right? Well, if cur.next currently points to the next node, and cur.next.next points to the node or node after, if we set cur.next to cur.next.next, we're essentially skipping the next node by setting curs.next field to come after the current next. Let's type it out. Hopefully that will make things a little clearer. So we simply set cur.next to cur.next.next. Isn't that cool? Power of references. And finally, we said we would return count. Let's see if this works. All right, so we're given the initial list 2, -4, 12, 0, 2, 2. All right, and it looks like we removed one of the 2s, but we're still missing 2. 2 2s are left. What happened? Let's try and debug what's going on here. Well, the first thing I noticed is that we're not incrementing count, so let's go ahead and take care of that when we were removing a node. But that was a minor bug. The main issue is our nodes, all of our nodes aren't being removed. Let's see if we're handling all of our four cases, our front, middle, and the empty cases. Well, okay, let's look at our front case. If our front has a 2, are we able to remove it? Well, it looks like we set cur the front, and then inside of our loop, we're always checking if cur.next.data is equal to val, never cur itself. So if our front had a value of 2 that we were trying to remove, we would never be able to remove it as we're never checking for it. So we need to handle this front case somehow. Let's do that. So we need to guarantee that front is not equal to null if we're looking to remove it. We're looking at that by using front is not equal to null. And we also want to check if front contains the value in order to remove it. If we want to remove the front node, we will set it to the next node. The two ways to manipulate a linked list are by using .next in front, and luckily enough we're dealing with front, so we can correctly manipulate it. So front is equal to front.next, just setting it to the next node, like we were doing down below. And we also need to increment counts. The last part is we're using a while loop instead of an if statement. So if we use an if statement, then if our front value was null, if our front value was equal to our value, we would remove it once. However, what if we had multiple 2s in a row, right? Well, the same issue would occur. We would set front to the next value, which is fine, as we removed one of the nodes we wanted to remove. But then we would exit out of this if statement with a 2 still in front. We'd run into the same bug. So we need to keep removing until we know for sure front doesn't contain the value we're looking to remove. Great. Let's look at the middle case. So if we're in the middle of our linked list and we're looking to remove a value, we need to make sure we're handling all cases. And it looks like the same pattern is occurring down here, where we're removing a node once if the not next data has the same value as the value we're trying to remove. However, if we remove one node, that'll all be it. That's all we're doing. If there were 2 sequential nodes that contained value as their data field, we wouldn't remove both. We would only remove one and then set current to current.next. So we need to be continually removing until we know for sure that we're setting cur to a node that does not contain the value we're looking to remove. And in this case, we also need a while loop. This is close. However, if we're continually setting .next, we might run into a case where we actually set .next to null, and then we could call .next or try to access the field of a null node. That will raise the null pointer exception. So we need to loop while the current.next.data is equal to val, and while current.next is not equal to null, right? And it's super important for this null check to come first, as we need to make sure that current.next is not equal to null in order to access this data field and check it over. Awesome. So that took care of the front case. That took care of the middle case. How about the null case? So if this were null, we would skip over this loop as front would be equal to null. We would set cur to be equal to front, or cur equal to null. And in our while loop, we would call cur.next on a null node. That's a null pointer exception. So we also need an additional check that cur is not equal to null first, before we check its null field, or its next field is not equal to null, in order to avoid a null pointer exception. Finally is the end case. What if the node we wanted to remove was at the end of the list? Well, this code takes care of it for us, as we're stopping one early, so we're always treating it as some sort of middle case, right? If the very last node happened to contain a 2, or its data happened to contain a 2 if we were looking to remove 2's, we would enter this for loop, and we set cur.next to cur.next.next. This would be 1 early, and cur.next.next would be equal to null. So we would just set the node before the very end of the list to null, or the net.next field to null, and we'd be perfectly fine. We never try to access the field of a null node. We would set current to current.next or current to node, and then this check would prevent us from trying to access a field of that null node. It would be a-okay. Let's run our program to see if it works. Oh, looks like I tried to compare front to val instead of front.data to val. Let me go ahead and make that fix. And boom, we get the desired behavior we wanted. Here's the solution in case you wanted to look at it a little more or maybe pause the video. And yeah, good luck on your quiz, I believe. And definitely do more of these ed practice problems for additional practice if needed. Have fun.